Rule number 5, the product rule. So we already have looked at what happens when you add or subtract functions, and we could take the derivative of each of them separately. So our logical guess then is if we are multiplying two functions together, then why shouldn't the derivative just be the derivative of one multiplied by the derivative of the other? Because if adding them was that simple, just do the derivative of one, add the derivative of the other, why can't multiplying be that simple? Okay? And this was exactly the same thing that Leibniz guessed. Let's think that that works. Okay? Unfortunately, his first guess, like many first mathematicians guess, when you try to do something simple, it doesn't work out. So here, if we took x and x to the 4, and those were our two functions, okay, you could multiply them together and actually simplify and get x to the 5, right? And the derivative of x to the 5 would just be 5x to the 4. That's the power rule. But if you did them separately, what's the derivative of f of x? It's 1. What's the derivative of x to the 4? It's 4x cubed. And if you just multiplied the two derivatives together, you would get 4x cubed, which doesn't match the actual answer of 5x to the 4. So the first guess of just multiplying them doesn't work. I'm pretty sure this was not his second guess. But after some work, he came up with this. Oh, well, if I have two things multiplied together and I want to find the derivative, I can go back. That was too quick. So here is what the rule is when you're multiplying two functions. You have, and I'm going to color code things here, you have one function multiplied by another function. The derivative rule says keep the first function the same, multiply by the derivative of the second function. Then keep the second function the same and multiply by the derivative of the first function. So we can see this in both Leibniz and Newton's notation. This is Newton's notation right here. In Leibniz notation, highlighting with the same colors, we just have a function u multiplied by a function v. We keep the first function the same and multiply by the derivative, dv dx, of the second function, plus then we keep the second function the same and multiply by the derivative of the first function. Okay? Keep the first one as is times the second plus the second one as is times the derivative of the first. And it doesn't matter the order, which one you keep the same and which one you do the derivative, because you're adding. So even if you forget the order, or it doesn't matter the order, just keep one the same, multiply by the derivative of the other one, then keep the other one the same and multiply the derivative of the first one. You put, like, a negative is just a coefficient, so that would just be included in one of them. No. You just put the negative with one of them. So if we wanted to do, right, I mean, I would hope you never take the derivative of x and x to the 4 like this. I hope you always multiply them out and get x to the 5. But if I was going to take the derivative of this, notation-wise, if I have a function, Leibniz notation, and I want to take the derivative, I can write this out in front. That means taking the derivative of this would equal, and I color code things the same way. My first function, color code in the same way. My first function in yellow, my second function in green, it says keep the first one the same. Multiply by the derivative of the second one. Plus, keep the second one the same. Multiply by the derivative of the first one. So again, I'll color code where I kept things the same. Here I kept the first one the same, and then I have the derivative of the green one. And here I kept the green one the same, and then I wrote the derivative of the first one. What are we going to get? 4x to the 4 plus an x to the 4, which is 5x to the 4. Of course, in this situation, you wouldn't want to do that. You would want to just multiply them first to make life easy to use the power rule, because the power rule is a lot easier. However, sometimes you have functions multiplied together that are not easy to simplify to get to the power rule. And so, the product rule becomes quite helpful. Okay? So we have to, when you see this, you have to decide, should I use my old rules, my power rules, or should I use my new rules? All right? If I use my new rules, okay, and again, at the beginning, I'm going to use lots of highlighting. My first function multiplied by my second function. I kept my first function the same, multiplied by the derivative. Then I kept my second function the same, multiplied by the derivative of the other one. If you wanted to simplify this, you can multiply things through, combine like terms, and you get 6x squared minus 2x. Could we have done this one using our old rules? Yes, because you could have distributed to begin with, right? Oh, this is other stuff. I'm not going to show you this. We could have distributed to begin with and got 2x cubed minus x squared. And then the derivative would be 6x squared minus 2x. Example 2. We have one function multiplied by another function. If we use our new product rule. Oh, I color-coded them backwards. Is that going to that's going to bother somebody. It's going to bother me. There, Cyclops. Yellow here, green second. There we go. Got to keep things consistent. Okay, so we keep our first function the same, multiplied by the derivative of the second. Then our second one stays the same, multiplied by the derivative of the first one. Again, this is where when you do calculus, it looks like magic, because they're simple little rules that if you know the rule, you can do it. But if someone's trying to look at what you're doing, they have no clue what's going on. And if you simplified this, we could distribute, combine your like terms, and get 25x to the 4 plus 3x squared. Again, can you see in this one that you could have used your old rules? If you distributed to begin with, you would get x cubed plus 5x to the 5. And then your simple derivative rules are 3x squared plus 25x to the 4. So in that case, I like the blue better. The blue is simpler, simpler to simplify, quicker, less to write. So sometimes just because you have a product rule doesn't mean you need to use it. You might want to simplify first. And that simplifying first might make your life easier. However, sometimes there's things that like, okay, I could FOIL this out, but now it's getting a little bit messy just to simplify. Maybe I want to use the product rule. So color coding things correctly. First function multiplied by second function. Keep the first function the same. Multiply by the derivative of the second function. Then keep the second function the same. And multiply by the derivative of the first function. Now, often on tests and exams, you do not even need to simplify. You're done. One line, you wrote your answer. This would be given full marks. No need to simplify. If we wanted to simplify because the answer at the back of the book is simplified, you could distribute, combine your like terms, and get your answer. Yes? Which part? This 6x minus 1? The 6x minus 1 is the derivative of the green. So I bring the 2 out in front to get 6x. The derivative of minus x is just minus 1. So the derivative of the yellow, bring the 3 out in front, you would get 6x, subtract 1 from the exponent, 6x squared. And the derivative of plus 5 would just be 0. So if you were just asked to find the derivative and you didn't need to simplify, you would just need to write line number 1 and you would be done. Then the product rule is probably the best. If the question said simplify in the end, then I might decide at the beginning I'm going to multiply this all out. 6x to the 5 minus 2x to the 4 plus 15x squared minus 5x. And do the derivative of that instead, which would be some of the times you do not need to simplify.